students, welcome to the linear Algebra One, coded as OMT 111. Now, in this lecture, we are going to see the knowledge area 60. And this knowledge area 60 entitled as rank, inverse of a matrix, and systems of linear equations. So, we are going to see these four subtopics: rank of a matrix, determinant of a matrix, inverse of a matrix, and systems of linear equations. Starting with the rank of a matrix. What's the rank of a matrix? Rank of a matrix is, let's say, rank of n times n matrix is the dimension or row space of the matrix A. Rank of a matrix A denoted by rank bracket A. The common approach of finding rank of a matrix is through row reduction. Okay, let's see an example. Going through this example just quickly, and then we come with calculations. Find the rank of the matrix A as given here. So we just reduce this matrix. And after reducing the matrix, we obtain that this matrix has the row with all 0 entries at the bottom. So this means that this row with all 0 entries was not linearly independent with other rows. So that's why I reduced it up to all 0 entries. So the remaining non-zero rows are just only 2. This one, let me have vector, this one, and this vector. So since there are only 2 non-zero rows, we say that, or we conclude that the rank of the matrix A is 2. Continuing with another example, the same procedure, we obtain that this matrix has no 0 row. So since all the row has 0 and non-zero entries, no row which has all 0 entries. So we count all of these, that 1, 2, 3, 4. There are 4 non-zero rows. So since therefore the rank it is 4, we come for the calculation. So let's see the determinant of the matrix. This is a second subtopic. Determinant of the matrix can be calculated only in square matrices. And the determinant of the matrix is denoted by just bracket A or the absolute of A. So what's the determinant? Is the number associated with A that describes certain property of matrix A. How can we find the matrix determinant? The matrix determinant can be obtained through 2 methods. There are general 2 methods. We can determine, or we can find the determinant of a matrix by using a formula, specific formula, and by using properties of the determinant function. Okay, using a formula. Let's say we are going to find the determinant of 2 by 2 matrix. We just multiply this product, this entry and this entry, we obtain this one, and we multiply this entry and this entry, we obtain this one. Then we minus, as it has described in this sketch here. Okay, or simply, determinant of this matrix with entries A, B, C, D, just take A times B minus C times B. Then you get the determinant. Okay, finding the determinant becomes so exhaustive as we have the matrix of the higher and the higher and the higher dimension. So that was 2 by 2 matrix. What about 3 by 3 matrix? 3 by 3 matrix, see, we just take the product of this one, this one, this one, plus we take these two rows here, then we take the product of this and this one, these products plus this product plus this product minus the product of this one, the product of this one, and the product of this one. This will give this one. So that's why we can find the determinant of a matrix in which is 3 by 3 matrix. We also see about 4 by 4 and so on, but the determinant of matrix cannot obtain in a matrix which is a square matrix. The following are the properties of determinants. Let's see the first one. If two rows of matrix are interchanged, the determinant of matrix will change its sign. If it is 2, it will be negative 2. The determinant of identity matrix, this is multiplicative identity matrix, will be 1, because we are going to see also the example. If we interchange also, you have said about interchanging of the rows, even the columns change the sign of the matrix. Okay, if the row is multiplied by a constant, then the determinant is multiplied by that constant, if it's just one row. Adding a multiple of one row to another leaves the determinant unchanged. For example, you have a matrix with entries A, B, and BC, a square matrix. If you take another row or another column, add it to another, then the determinant will be the same. Determinant of a triangular matrix is equal to the product of diagonal entries. Okay, we are going to see what's a triangular matrix. If the matrix has 0 row, then the determinant will be 0. Property number 6. Property number 7. If A and B are square matrices of the same size, then the determinant of matrix A times B is equal to the determinant of A times the determinant of B. Property number 8. If A is n times any matrix, and alpha is a scalar or any real number, and the determinant of A equal to B, then the determinant of the matrix of alpha times A equal to A power n, the size of this matrix, take us from the size of the matrix, times the determinant of A. So, look here, we have said that the determinant can be calculated or computed using two methods: specific formula and the properties of determinants. So these are specific formulas. These are specific formulas, just specific formulas. And using these properties, we can find the determinant of another matrix. So this is the finding by using properties of determinant function. For example, you have a matrix, identity matrix, and you're asking to find its identity. Okay, we know by the properties of identity matrix that the determinant of identity matrix is 1. So we don't need to calculate, we just use the properties. That the determinant of identity matrix is 1. Now, the identity matrix are the determinant of 1. As well as this one. For example, let me talk about property number 8. You have the determinant of A. You're asking to find the determinant of alpha times A. We just take it, the determinant of A times alpha power n. N is the size of that matrix. If it is 3 by 3, then you take alpha power 3 times the determinant of A. Then you get the determinant of alpha times A. Okay, these are different examples of determining determinants of matrices. Okay, I'll come next to show different examples through calculations. So let's go to the next topic or subtopic called inverse of a matrix. So what's inverse of a matrix? By definition here, if I have a square matrix, of course you cannot find the inverse of a non-square matrix. If I have a square matrix A, we can find another matrix of the same size called B. If matrix B times A, as well as swapping them, B times A and A times B are equal, and the result comes ident matrix. So we say A is inverse matrix of B and B is the inverse matrix of A. If you cannot find such matrix B, that if you multiply with A gives an ident matrix, that matrix is called a singular matrix. Also, a matrix with zero determinant cannot have its inverse. So we can also say that matrices of zero determinants are also singular matrices because they have no inverse matrices. Okay, generalizing that if you have matrix a square matrix with any greater than 2, then the inverse of A times power, exponent n, is equal to A exponent negative L. Because, okay, let's see an example. I'm given a matrix A. We ask it to find the range of A, determinant of A, and determinant of 2 times A. Solution. We find the determinant of a matrix A by using row reduction. So just writing 2, 1, 2, 3, 1, 1, 1, 2, 4, 6. This is acting as a pivot. Okay, to reduce this one into 0, you just take R2, you go to R1, and as R2. So R1 remains as it is 1, 2, 3. Here it will be 0. This one and this one is 0. This one and this one is 1. 3 minus 1 is 2. And also for row 3, it's 2 R1 and R3. So if you take 2 times 1 is 2 minus 2 is 0. 2 times 2 is 4. 4 minus 4 is 0. And 3 times 2 is 6. 6 minus 6 is 0. Okay. So dear students, after reviewing this matrix, in echelon form, the row at the bottom has all 0 entries. Now, the non-zero rows are just the first row and the second row, and there are only 2. Since non-zero rows are only 2. One, 2, 3, and 0, 1, 2. Therefore, the rank of matrix A is equal to 2. Okay, this was A. Let's B. We asked to find the determinant of A. determinant of A equal to then this way you just put your plus minus plus. So we start with 1. 1, you have this column and this row, you make this 1, 1, 4, 6. And here's negative, you put negative 2. You have this column and row, you make this 1, 1, 2, 6. And then last you have 3 times, you have this row in the column, you make this 1, 1, 2, 4. So this can be used even in the matrix of 4 by 4, 5 by 5, 6 and by 6. But it will take a lot of time to compute. But you use the same as if it's 4 by 4, you just plus, minus, and the minus will be of 3 by 3, but here 2 by 2. You find the determinants. Okay, here's 1 times the determinant of this. 1 times 60 is 60 minus 4 times 1 is 6 minus 4 minus 2. 4 times 1 is 6 minus 2 times 1 is 2 plus 3. 4 times 1 is 4 minus 2 times 1 is 2. So what do we get here? 6 minus 4, it is 2 times 1 is 2 minus 2 times 6 minus 2 is 4, so it times 4 plus 3 times 4 minus 2 is 2. Okay, here is 2, here is 8, and here is 6. If you add these two matrices, it gives us 0. Gives us 0. So the determinant here is 0. So therefore, okay, after computing this determinant of the matrix A, we have obtained that the matrix A and the determinant of 0. Okay, let's see part C. To find the determinant of 2 times A. Remember, my dear students, that the determinant of A has been obtained by using the formula. But the determinant of 2A, it's not necessary to go through the formula. We just use the properties of determinant. Part C. We need to find the determinant of 2 times A. Okay. Since A is and 3, since A is a 3 by 3 matrix. Now, determinant of A, 3 times A, equal to 3, determinant of 2 times A, 2A, equal to 2 exponent 3 times determinant of A. So, if you find 2 exponent 3, you will get 8. 2 exponent 3, you get it is 8 times determinant of A. And the determinant of A is 0. So this will be 0. Therefore, determinant of 2 times A through properties of determinant also is equal to 3. Dear students, as I've said, that this is part 6. You are going to see how we are going to start solving the system of linear equations by using rod reduction, which is categorized into 2 by Roy-Cohen form, which is Gaussian elimination method, and reduce it to a current form, which is Gaussian-Jordan elimination method. Okay, starting with Gaussian elimination method. Gaussian elimination method is a method of solving systems of linear equations by reducing the argumentative matrix of the system into a column form, into raw echelon form. For example, we have just given this simple system of linear equations. So we are going to solve this one by using Gauss elimination method. So that steps that which we are required to pass through to solve this system of linear equations. So step 1, we create a argumented matrix of the system. The first matrix is formed from the entries or the coefficients of the variables or the non-numbers x, y, x and y. So from the first equation, we have 2 and 1, 2 and 1, and the second we have 1 and 2. So these are added here to form argumentative matrix. So after forming this argumentative matrix, what followed next? We reduce the argumentative matrix into raw echelon form. So we start by reducing into raw echelon form. After reducing, we get here. So we get this matrix, the argumentative matrix with entry 1, half, 1 and 0, and also with this one also as reduced to 5 over 2 and 1 over 3. So then we go to back substitution. Back substitution is substituting back to this system by using this matrix and this matrix here. So we get this one here. So now it's simple. We multiply this matrix with this vector, whereby it's 1 times x, we get x, half times y, we get 1 over 2 times y, which equals this one, the corresponding edge of the vector at the right hand. And also, 0 times x is 0, and then 1 times y is y, equal to 1 over 3 here. So now we have already obtained the value of y, and we substitute this question to get the value of x. Now substituting, we obtain x equal to 7 over 3, and y equal to 1 over 3. So that was the system of equation with 2 equations and 2 unknown numbers. So let's see another example, the system of linear equation with 3 equations and 3 unknown numbers. So it is this one here. The same procedure is applied as you have seen the first example by creating argumentative matrix. So this matrix is formed from the coefficients. I mean the coefficients of the variable x, y, and z. And this vector here, which is appended here, is formed from these numbers here, 2, these constants, 2, 3, and 1. So we reduce also this one into raw echelon form. After reducing, remember that when we are reducing this matrix, we use the same, we simultaneously reduce this vector here, and we get this one here. So next is back substitution. We take this matrix here, and the vector which was x, y, and z equal to this vector obtained here. So you multiply this one with this one, we get this one here, this one, we get this one here, and this with this one, we get z with this one here. So we equate with this respectively, 2, negative 1, 1 over 3. So the last give us z, this one. So substituting back this one, you get 1, substitute back here, you get the value of x. So, my dear students, solving a system of linear equation by using Gauss elimination method is solving by using the raw echelon form. Next part, or next way of solving the system of linear equation by using raw reduction is by using Gauss-Jordan elimination method. What Gauss-Jordan elimination method? Is a method of solving the system of any question by reducing the arithmetic matrix into reducibly raw echelon form. So, this is an example. Solve the following system of any question by Gauss elimination method. I think I was supposed to write it by Gauss-Jordan elimination method. So, which is by using this raw echelon form. So, we follow the same procedure, but what is different here? We reduce to reduce the raw echelon form. So, for example, starting with A, we create a arithmetic matrix. We reduce it into reduce the raw echelon form. We get up to here, and then by back substitution, we get directly the values of x and y. The same as this one also, and we reduce up to reduce the raw echelon form. We get this one here. We go to back substitution, directly we get the values of x and y. So let's go to see just one example by calculation. Okay, students, let's see an example. We are asking to find or to solve this system of linear equations by using Gaussian Jordan elimination method. Okay, solution. The first step is putting this system into matrix, into arithmetic matrix. Arithmetic matrix is taking the matrix form here by using these variables, or these are knowns, taking their respective coefficients, append with this vector, which is formed by these constants. So, solving by using Gaussian Jordan elimination is solving this system by introducing the raw echelon form. So, let's start to reduce this one and to reduce the raw echelon form. Taking this as a pivot, because this has already started with 1, so we just take it. The second row will be 2 R1 minus R2, and the third row will be just R1 minus R3. So if you come here, this 1, this 0, this 1. The first row remains as it is. So the change appears at the row 2 and row 3. So if we take 2 times every entry in the first row minus the second row, here we get 0. Here we get 3. Sorry. Here it's 2 times 2 is 4 minus 1. Yeah, sure. It is 3. Then 2 times 1 is 2 minus 3 is negative 1. And then 4 times 2 is 8 minus 60 is 2. Next thing, the third row, just taking the first row minus the third row. Here you get 0. Y minus 1 is 0, 2 minus 1 is 1, 1 minus 1 is 0, and 4 minus 3 is 1. Again, next, remember, we are reducing this one into reduce the raw echelon form. So I want to get this one to be 1 here. So take R2 equal to 1 over 3 R2. So here is 1, 2, 1. And this will be 4. Then here is 0, it will be 1. Then 1 over 3 is 2 over 3. So this will be made 0, 1, 0, 1. So this is the reading entry, which is 1. So we need also the third row to have the reading entry, which is 1, and in its column should be at the right of the reading entry of the previous row, which is supposed to appear somewhere here or the other place. So we have to reduce this one, taking this as a pivot. So to get to row 3, we just take row 2 minus row 3. Basing on the pivot. So here is 1, 2, 1. Here is 4. Yeah, and this will remain the same, 1 over 3 and 2 over 3. So taking here is 0, 1 minus 1 is 0. If you take this one and this one, you get 1, negative 1 over 3. And this one and this one, you get negative 4. I mean it's 1 over 3. I think it's sure it's 1 over 3. So again, so we need this one to appear as 1. So next here, from here, R3, we got negative 3 times R3. Here we are just reducing firstly into right quadrant form, and next we go to reduce right quadrant form. So this one here, it's 1, it's 2, it's 1, and here it's 4. Again, here is 0, it's 1, negative 1 over 3, 2 over 3. This is 0, this is 0, this is 1, and this is 1. So, dear students, remember, reducing into this zero column form, we have to make sure that every reading entry in its column should be under the non-zero number. So we have to use this one here and to use this with respect to this one. Okay, let's continue, my dear students. Let's wrap here. Of course, you know what you're doing. You're solving this one using the destroy column form. So, next here, we need to reduce this one to become 0. So, this is acting as a pivot. So we put here 0. This will be 0. This will be 1. That's it, negative 1 over 3. Because this is the pivot, negative 2 over 3. So, what should we do this one to be 0? We just take negative 2 times this one plus this one. So, R1 equals negative 2 times R2 plus R1. So, negative 2 times 0 is 0, plus 1 is 1. Negative 2 times this one is 1, negative 2 plus 2 will be 0. Negative 2 times this one will be 2 over 3 plus 1. 2 over 3 plus 1 will be 3 here. Is 2 plus 3, which is 5 over 3. Okay, so this 5 over 3. Here I get 5 over 3. And again, we multiply negative 2 with this one to get negative 4 over 3. We plus 4, which is over 1. So here 3, negative 4 plus 12, which is 8 over 3. Of course, here is 8 over 3. And this will remain as it is 0, 0, 1, and here it is 1. Okay, now what we are going to do, we are going to reduce this one and this one with respect this to this one as a pivot, because this reading entry in its column supposed to be the only non-zero number. So, reducing, remember to start with this one, 0, 0, 1, and there is 1. So, to eliminate this one, you just taking, to get R2, it's just taking 1 over 3, R3 plus R2. So, this 0 plus 0 will be 0, 0 plus 1 will be 1, and 1 over 3 is 1 over 3. 1 over 3 plus negative 1 over 3 is 0. And also here, 1 over 3 plus 2 over 3 will be 1. Again, for the first row, which is R1, we want to eliminate this one here. So it's just taking negative 5 over 3 ada 3, ada 1. So 0 times negative 5 over 3 will be 0, plus 1 will be 1. 0 times negative 5 over 3 will be 0, plus 0 will be 0. 0 times, negative 5 over 3 times 1 is negative 5 over 3, plus 5 over 3 will be 0. And again here, negative 5 over 3 times 1 is negative 5 over 3, plus 8 over 3. This will be 3 over 3, which is equal to 1. So also here is 1. Remember, my dear students, that if we have asked you to reduce or to use Gauss elimination method, which is reducing up to row echelon form, we could end up here and go to the next step, which is back substitution. But because we have asked you to use Gauss-Jordan elimination method, so we should go to reduced row echelon form, which is this one. So now we are in reduced row echelon form. The next step is to put to back substitution. So take back substitution. This is the matrix of 10, 1, 0 after reduced row echelon form. We multiply here x, y, and z equal to 1, 1, 1. So by back substitution, this times this row times each of the corresponding entries of this one, we get just x 0, 1 times x, 0 times y 0, 0 times z is 0, so which is equal to the corresponding entry, which is 1. So the same one here, we get just 1 times y, the rest will be 0, so equal to 1 here. And here, 0 times x is 0, 0 times y is 0, 1 times z is z, which is equal to 1. Now, these are the values of x, y, and z after solving the system of linear equation by using Gauss-Jordan elimination method. Okay, students, after we have seen by using row echelon form, by using reduced row echelon form, we have seen that the row reduction can be used in solving systems of linear equation. This is what you have seen through calculations. And this is the end of this lecture, concentrating only on the knowledge area 60. Thank you so much for your attention.